Hello everyone, welcome back. Today I'll be starting our video with an interesting question. Did you know that artificial muscles can lift up to 1,000 times their weight? That's really impressive for a technology that is in early development. Now let's see what these artificial muscles really are and if they can replace human muscles. Let's start by talking about what the term artificial muscles means. Artificial muscles are human muscle-like structures that can vary in their types. Some are light and powerful, while others are a bit heavier and more powerful. Unlike biological muscles, these materials use an impressive amount of mechanisms to produce force and motion. In an experiment, the artificial muscle managed to lift a 1 kilogram dumbbell and proved 17 times stronger strength in comparison to a human muscle. Now we'll continue with the history of artificial muscles. The first artificial muscle was developed by Joseph Loves McKibben back in the 1950s. This artificial muscle was developed from rubber, which was placed in several threads along a longitudinal axis, enabling it to contract the lateral restriction of the threads. After the development of the first artificial muscle, companies began exploring different technologies and started making their own artificial muscles. Even well-known universities like MIT and Harvard are working on these artificial muscles. This shows that in the future, artificial muscles may be an important aspect of our lives. Now we can talk about different types of artificial muscles and their functions. Artificial muscles can be divided into three major groups based on their actuation mechanism. These groups are electroactive polymers, pneumatic artificial muscles, and thermal actuation. Let's start with electroactive polymers, or shortly EAPs, which represent a class of materials that respond to electrical force with mechanical deformation. Consider a polymer that contracts or expands depending on the applied stress. This is the essence of EAPs. Piezoelectric polymers, for example, are good at converting mechanical stress into electrical signals, making them ideal for sensors and energy harvesting applications. However, their limited torque output and the lack of a universally accepted material create challenges in their widespread use as an artificial muscle. The electric elastomers, or DEAs, work based on electrostatic forces induced by an applied electric field. They can undergo large deformations, making them promising candidates for soft robots and applications requiring complex movements. However, their low torque movement ability remains a limitation that prevents their widespread acceptance as powerful artificial muscles. Electrorestrictive graft elastomers offer another avenue with the EAP family. These materials undergo deformation due to volume change resulting from the alignment of molecular dipoles under an electric field. While they offer advantages in terms of flexibility and lightweight design, limited torque outputs are still a challenge for applications requiring higher mechanical performance. Liquid crystal elastomers, or LCEs, are a unique class of electroactive polymers that combine the properties of liquid crystals and elastomers. These materials exhibit significant shape changes in response to electric fields, showing promise for soft robotics and adaptive optics applications. However, addressing low torque capabilities is vital to increase their utility in artificial muscle technology. Secondly, let's go deeper into the ferroelectric polymers group. Ferroelectric polymers, characterized by natural electrical polarization, are also a type that is in EAP applications. These materials can undergo reversible deformations in response to electric fields, providing opportunities for advanced actuation and sensing devices. Despite these promising properties, the lack of a standardized material for EAP devices creates difficulties in their use. Significant advances have been made in EAP technology since the 1990s. Researchers and engineers continue to explore new materials, manufacturing techniques, and applications to address the limitations of current EAPs. The search for a standardized material for EAP devices remains the main focus in achieving widespread use and integration of these unique materials into various technological fields. Moving away from electroactive polymers, pneumatic artificial muscles, or shortly PAMs, offer a different approach. Think of an inflatable balloon. Rather than being a basic toy, it is used to create controlled contractions. While the material that is used in the production of PAMs is different than normal plastic that is used in the production of balloons, PAMs rely on compressed air to inflate internal sacs, converting the resulting expansion into precise linear movements. The complex design of PAMs, which includes braided wires and special membranes, provides extraordinary control over both movement and force. As a classic example, the muscle that McKibben made demonstrate their versatility, especially in prosthetics, exoskeletons, and even industrial automation. Still, achieving higher force output and miniaturization are still ongoing challenges. Now let's talk about the thermal actuation section. The field of thermal actuation offers another avenue for artificial muscles. These artificial muscles can be created with readily available materials, such as fishing lines or sieving thread. Creating artificial muscles from these everyday materials that exhibit extraordinary strength and power that exceed their biological counterparts by 100-fold makes it really cheap and accessible. This cost-effective approach offers exciting applications, such as self-closing windows powered by temperature changes. Similarly, processing materials at the nanoscale, as seen in carbon nanotube muscles, opens the door to extraordinary capabilities and miniaturization potential. Shape memory alloys and liquid crystal elastomers, which use heat to induce shape changes, further expand the scope of thermal actuation possibilities. Despite these remarkable advances, artificial muscles still face obstacles. Limited power output, efficiency concerns, and difficulties in miniaturization are common across a variety of technologies. Additionally, the lack of standardized material for specific approaches hinders widespread commercialization. But the future of this field is full of optimism. Researchers are constantly investigating new materials, manufacturing techniques, and actuation mechanisms to push the boundaries of performance and functionality. Advances in fields such as nanotechnology and material science have tremendous potential to overcome current limitations. In conclusion, artificial muscles have been improving over the past 55 years. These improvements include more powerful and lighter artificial muscles. As of today, artificial muscles cannot replace human muscles, as they cannot mimic the movements of human muscles. With 3 different types, artificial muscles can be utilized for various purposes. Some are used in machines, while others are still being tested in labs. So, can these muscles be used to help disabled people? Only time will tell. This is the end of our video. Thanks for watching. As always, it was Hefsel Times.